Hey everyone. Every single day we're sending emails, streaming movies, saving our most precious photos, and we just trust that it all works. We trust that our data gets where it's going and stays exactly the way we sent it. But behind the scenes, there's this invisible, constant battle being fought to stop all that data from turning into complete nonsense. Today we're going to pull back the curtain on that unseen guardian of our digital world. So what is it? What's stopping your vacation photos from turning into digital static? It's a question you've probably never even thought to ask, right? And honestly, that's the amazing part. It's because a set of incredibly clever, kind of beautiful mathematical tricks are working tirelessly behind the scenes to make everything just work. So let's dive in and see how they pull it off. Okay, so to really appreciate the solution, we first have to understand the problem. We have to meet the enemy. And in the digital world, the enemy is this constant, invisible force called data corruption. I mean, think about it. When your phone sends a text, that's a physical signal flying through the air. When you save a file, it's a magnetic change on a disk. And those physical things can get messed with by anything, from a solar flare to, your microwave oven. We call these disruptions noise, and all they do is flip a digital 1 to a 0 or a 0 to a 1. And that one tiny flip can lead to a corrupted photo or even a massive system failure. And this isn't some rare glitch, you guys. It's a constant, relentless threat. So how in the world do we fight back against something that's always happening? Well, the answer is a beautifully simple, elegant idea: redundancy. That's it. All we do is we intentionally add a little bit of extra, carefully designed information to our data. Now, this extra data isn't new information. Its only job is to be an insurance policy for the real information.
And this whole redundancy thing, it gives us two powerful levels of defense. First up, you've got error detection. Think of that like a smoke alarm. It just screams, hey, something's wrong here, something's not right. But then you've got error correction, and that's the real game changer. That's like the fire department. They don't just hear the alarm. They know exactly which room the fire is in, and they've got the hose ready to put it out.
All right, let's start with that first level of defense, just spotting the mistake. We're going to look at the simplest, most fundamental tool in the toolbox. It's called the parity bit.
So check out how simple yet smart this is. Let's say we want to send the data 1011. Before we send anything, we both agree to a rule: even parity. All that means is the total number of ones we send has to be an even number, always. So we look at our data, 1011. We count the ones, 1, 2, 3. That's odd. So to make it even, we just stick an extra 1 on the end. Our new message is 10111. Now it has 4 ones. That's even. If just one of those bits gets flipped by noise on its journey, the receiver will count the ones, get an odd number, and know instantly, whoa, hold on, this data is corrupt. So simple but so effective.
But knowing there's a problem is only half the battle. What about actually fixing it on the spot? For that, we've got to level up. We need a much more powerful technique, and that's where the Hamming code comes in.
The Hamming 7.4 code is an absolute classic, and for a good reason. It's so efficient. It takes just 4 bits of your actual data, and it protects them by adding only 3 extra parity bits. And with just those 3 extra bits, it can not only tell that an error happened, it can figure out the exact location of the bad bit. The whole secret is in this incredibly clever structure. So just look at this for a second. See how each parity bit, P1, P2, and P3, is responsible for checking a unique but overlapping group of the data bits. Like P1 keeps an eye on bits 3, 5, and 7. P2 watches 3, 6, and 7. They share some duties, but not all of them. This specific pattern of overlap, it's not random at all. It is the absolute key to the whole magic trick.
Right, so the setup is smart, but how does it actually work? How does this web of overlapping checks let us find the one single bad bit out of the whole group of 7?
Well, the process is called syndrome decoding, and it's basically like detective work. When the message arrives, the receiver reruns all the parity checks. Then it compares its results with the parity bits that were sent. If a check fails, it gets a 1. If it passes, it gets a 0. The combination of those failures creates a unique binary number, the syndrome. And this number, this is the magic part. This syndrome number is literally the address, the exact position of the bit that got flipped. Once it knows the location, the system just flips the bit back and bam, data fixed. It's incredible. Now, this all might sound like old news, right? Cool, but settled science. Well, get this. These fundamental ideas are more relevant today than they have ever been. They are literally the blueprint for projecting the next great leap in technology: quantum computers.
It's the exact same core principle of redundancy that's at the heart of quantum error correction.
Now, the challenge is way, way bigger, because quantum bits, or qubits, are unbelievably fragile. They're exponentially more sensitive to noise than are plain old classical bits. But the solutions being built to protect them are direct descendants of what we just talked about. The basic logic of using extra, redundant information to find and fix errors is what's going to make reliable quantum computing possible.
It really all comes down to this. If you want to build the revolutionary computers of the future, you first have to master these elegant, foundational ideas from the past. This isn't just theory. It's the essential toolkit for making that next giant leap a reality.
So at the end of the day, it all boils down to the power of one simple idea: redundancy. It is the invisible, unsung hero of the information age. It's the force that makes sure your text messages make sense, your bank account is accurate, and this entire digital world that we all depend on remains stable and trustworthy.
And that kind of leaves us with one final thought. All of these amazing solutions came from simple logic and math. They built the world we live in now, and they're laying the foundation for the quantum world of tomorrow. It just makes you wonder, right? What other huge challenges can we solve, and what incredible new worlds will we build with the next simple, brilliant idea?